Hi, I'm Daniel, and with my colleagues we will be presenting our concept vehicle for the mechanical experimental engineering assignment. The repeatable vehicle we designed will be powered by energy stored in a series of springs. The linear movement from the springs will be converted into rotational using the rack and pinion principle, with the pinion acting as a shaft for our car. Since our shaft will be positioned longitudinal to the car, we will use another set of gears to transfer the movement to the wheel's axle. This explains the forward movement. Let's have a look how the car is going to do the return journey. As you can see in the image, we are using a pair of springs for every rack that moves the car forward. In reality, only one spring per rack would be enough to push you to the target, but we are using additional springs to load the rack for the return journey. As the shaft rotates, it is pulling the single spring racks into the opposite direction of the first one. You might wonder how does our vehicle know when it hit the target so it can return to the origin. Let's have a look at that. By now you probably noticed that the shaft is divided into two sections. One is for the forward movement and the second one is for the return. They are initially linked together by a gear, but there is a compression spring forcing the half of the shaft to separate from the other half. The separation, however, is blocked by a small latch at the front. This latch is being pulled downwards by an expansion spring. Again, this downward movement is blocked by a release mechanism, which is activated when the target hits the wall. This means that when the target is hit, the half of the shaft driving the car forward is disengaged, leaving only the single spring racks connected to the wheel's axle, making it move backwards to the departure point.
Hi, my name is Luis, and I'm going to speak about how the forces are going to interact in our vehicle. Roughly, half of the energy stored in the forward springs is going to use to move the vehicle in the other side. We have added a calculated efficiency of 80%. That is why we need some more energy in the forward side to compensate for this lost energy in the transfer. Calculating the initial torque we need in both ways and the maximum distance we have to achieve, we have come to some of this table and make a selection of the springs we can use for a vehicle. Changing some of the variables in our database, we can achieve different distances in powered vehicles with the different masses. With a connection of ratio of 2 to 1 between the crankshaft and the vehicle and the wheel axle, we will achieve 2 turns of the wheel for each turn of the crankshaft. Using mechanical connections and reducing the transmissions, we improve the efficiency of the energy transfer, which is the basic principle of our model. Once we can make a test in our model, we will be able to improve this efficiency and have more certain calculations.
Hi, my name is Elliot and I'm going to be talking you through the design selection process. In our initial brainstorm, we highlighted 3 possible means of propelling our vehicle. Our options were to use an electrical DC motor, the elastic potential energy in springs, or elastic bands. In order to determine which method would be the most effective in relation to our design brief, we discussed advantages and disadvantages as a group, allowing us then to make a selection table that can be seen behind us. That's allowed us to compare each method to a set of criteria which came directly from our brief.
I'm Dan, and as you can see from the results, the method of propulsion that was calculated to be most effective was to use springs, because of its properties allowing controlled release of energy with accurate calculations, enabling us to achieve our set parameters. Using elastic bands would have provided an erratic and less controlled release of energy, which would result in reduced efficiency due to energy losses. We decided against the use of an electric DC motor, as even though it would be simplistic, it would remove the ingenuity and design that could be achieved with a complex mechanical system such as the one that we have designed. From our research, we came to the conclusion that using springs for propulsion was the best suited method, as there is very little energy loss. Furthermore, the potential energy stored can be easily controlled. The means of using a spring-loaded rack and pinion assembly allows the potential energy to be converted into rotational energy to drive the vehicle's wheels. The release of energy can be controlled by using different spring rates, and in the example of our design, the potential energy is released at different stages to aid in controlling the rotational speed, as well as the torque transfer to the rack and pinion. This design also allows the springs for the secondary stage to be loaded as the vehicle is travelling forward. The rotational energy of the drive shaft is converted into elastic potential energy as the secondary springs extend. Once the vehicle has made contact with the outer boundary during the experiment, a switch will disengage the primary section of the drive shaft, propelling it in the opposite direction towards the starting point.
One of the features that we needed to consider when designing our vehicle was the cost. From the assignment brief we are given, a budget of £25 for all the components and manufacture of our vehicle. For the main body of the vehicle, including the wheels, we are going to use 3 mm thick acrylic. We use table shown next to me in order to decide exactly what springs we wanted by comparing the spring rates and the total extension. Each spring is then supported by a 2 mm steel rod, and the wheel axle is 3 mm acrylic rod. Altogether, the cost of the design was £24.30.